In this video, we will be talking about Lagrange error bound. Let's first review a Taylor series. A Taylor series uses a polynomial to estimate an actual function at a given point. So we know a Taylor polynomial uses this pattern to approximate a function. This Taylor polynomial estimates a function at a given x equals a. So now, where does error come in? An error will come in because, well, we know an error is a mistake. And in this sense, since we're estimating a function, we know that the error will be the actual minus an initial. So in this sense, it would be where f of x is our actual function and p of x is our Taylor approximation. And we use an absolute value because this is a magnitude. We don't want a negative because magnitude will give us the amount of an error. So let's look at a quick example of an error in a function.
Here we have an example of a function 1 over 1 minus x, and its Taylor approximation to the third order using the Coulomb series 1 plus x squared. And we can see that it estimates at that point 0, x equals a, which is 0, that it perfectly aligns with that approximation. But if we eyeball it from here, we can see that it's a good approximation between these boundaries. But there is an actual error, and that error can be seen if we zoom in. So we can see from the red that this is our actual function, and this is our approximation. And there is an actual error between these two as we move out from x equals a, and in this case, x equals 0.
We know an actual error can be found by using the actual function value minus the Taylor approximation, and we can rewrite this error as r sub of n using absolute values because they're still one magnitude. Now, we use Lagrange error for an estimation to estimate this exact value, and this is how we substitute it. Now, we know that this f plus n, we use f to the n plus 1 and x minus a n plus 1 and n plus 1 factorial instead of this, which looks strikingly similar to our Taylor approximation, because we want the error to be less than or equal to the next term in the series. And we use the next term because, well, we know that if we go up to the next term, it should be greater than this approximation. Well, because we're going up in degree of polynomial. And that's why we use the next term in Lagrange. So here we have an example where we will use Lagrange error to estimate an error bound. So let's look at the question. The f of x equals the sine of x squared plus cosine of x. And the graph y equals f at the fifth derivative of x is shown to the left, right here. So the question asks, let p sub 4 of x, which is our Taylor approximation to the fourth degree polynomial for f about of x, using the graph to show that p sub 4 over 1 over 4 minus 1/4 of x, absolute value, is less than 1 over 3,000. Now, before we even begin applying this to this formula, let's first look at the givens that we have. So first we know that we want it to be less than 1 over 3,000. Well, let's look at some similarities between this and this. So we have this right here, which looks something like what we talked before of what an actual error is. An actual error is f of x minus p of x, which looks exactly the same. So in other words, it will be r of n. So our r of n is p over 4, 1 over 4 minus f 1 over 4, f to the 1 over 4. So we know that this has to be, we have to prove that this error has to be less than 1 over 3,000. So which means our error bound has to be less than this value, which in other terms means that our error bound, let's just put this right here, bound, is less than 1 over 3,000. Well, now what we have to do is prove this. So first, we have to show that we have the next term. And, well, the question already gave it to us. We have the next term. We have f to the fifth derivative. Well, the question gave us to the fourth degree, and they're giving us the next derivative, which means we have to find the maximum value from this. And remember, that maximum value is this, f to the n plus 1 at a given z between x and a. And our a would be 1/4, x at 0, a at 1/4. And we're trying to find a maximum value at that given point to solve for this equation. Well, we know that x minus a is 1/4 because they're already given to us that at p sub 4 at 1/4. So we know one piece of our error bound already. So let's look at that first. To the n plus 1, which will be to the fifth, because, well, they told us the fourth degree, 4 plus 1, 5, all over 4 plus 1 factorial. Now, the only problem we're going to have to solve here is, well, what is this number? Well, this is our max. So remember, f to the n plus 1 at z is a max. And since we have this graph of f to the fifth degree, we can find the max between x and a. So this is x, this is a. And the max would be, well, we can see the function is increasing. And between those two boundaries, our max is at 40. This is an estimation, which is around 40. So we said at 1/4, we know that it is 40. So, well, guess what? We already have this number right here. So we can write that out as this. So now we have our error sub n, which is our actual error, is less than or equal to 40, because, well, now we found the max. So just 40 times 1/4 to the fifth, all over 5 factorial. And we have to prove that this number right here is less than 1 over 3,000. So 1 over 3,000. Well, let's simplify this. So we've proven that by simplifying this, our actual error is less than 1 over 3,000, 1 over 3072. So this proves that using our maximum value from this graph up to the fifth degree, that we're able to show that that error is less than what the question is asking. And this is how we can use Lagrange error bound to solve this.